Uh, Hello, everyone. Welcome to the tutorial on Active Inference Controller for Dynamic Systems. I'm Ajith Anil Meera. I'm a postdoctoral researcher at the Radboud University under Pablo Lanilos. I did my PhD in TU Delft under Martin Weser, who is also here. The whole point of this tutorial is to get to you to familiarize with how to apply Active Inference Controller into continuous time dynamic systems. Yeah. So when you apply active inference into robots, you would typically see something like this, where you have a target goal where you want it to go, and then your active inference controller enables your robot arm or something to go there. So this is one of the typical applications of active inference in robots in continuous systems. So in this tutorial, what I would expect you, once we are done with the tutorial, what I would expect you to know is how would you do something similar to this? In a more simpler representations, but at the end, the methodology that you have to follow to get here would be what would be covered in this tutorial. So I'm going to follow this methodology throughout, where you will take a dynamic system and you will model it first, and then you will absorb the differential equations out of it, and then either do linearization on the differential equations, or you transform it into the required stuff that you wanted to control a robot, for example. And then you discretize the whole equation that you have. And at the end, you design a controller. You might be wondering why the controller design is just at the end and there's a bunch of other stuff here. But the important part is that in order to do a controller design, you need all these things to get from a physical system to actually controlling it. You need to go through a lot of things before that. Yeah. At the end, you can summarize something like it's the physics part that comes first. When you get a physical system like a robot or something that moves, the physics comes first. And then you follow towards the math part of it, and then you have some sort of controller designed. At the end, we would be solving on something like this, a spring mass damper system. We are going to control that system. It is representative of a lot of physical systems in mechanical engineering, for example. At the end, you're going to go through some math, which you might or might not understand, but hold on, because at the end, everything that we are going to talk is going to reduce into 5 lines of code. That's it. 5 lines of code in MATLAB, and you would be able to make active inference controller that can control the kind of every, it's a big promise, but kind of most systems that you can control. So yeah, even if it's a lot of math, just hold on, because at the end, it's just 5 lines of code done right. That's the thing. If you miss one of these, good luck. So coming to the modeling part, in mechanical system, the very first step that you have to take when you see a robot or a physical system is to derive the equations of motion of that particular dynamic system. In this case, we have something like a spring mass damper system where there's a mass and there's a spring and there's a damper. I hope you understand the properties of these. A spring does what spring can do. A damper would do what damper can do, like friction, for example. And a mass would simply have inertia to move around. And then you apply a force F, and then it just moves to distance x. As simple as that. This is the most simplest mechanical dynamic system that you can find. And the first step you do is you draw something called free body diagram of it, where you label all the forces, that is being forces and moments. But in this case, we only have forces. So there is a force F in this direction, and then the spring is exerting a force of Kx. And then the damper is also exerting a force of V into x dot, which is the derivative of x, which is a velocity. What you do is you first draw the free body diagram. The second step would be to understand what's going on. In the first case, it's a static system where if you balance all the equation that you see here, which is F minus Bx because Bx is in the opposite direction, Kx minus Kx because Kx is in the opposite direction. So if you do that, if it sums to 0, then it's a static system. That's the definition. Now, there comes a difference where there's a dynamic system where it actually has an acceleration. The whole force is not balanced, but it is actually moving. If the body is actually moving, it has mass into acceleration term. So now you have a dynamic system, and in doing so, you now converted a dynamic system, and you have found the governing equations of motion. So what you got at the end here is what governs the motion of the whole block of mass connected to blah, blah. Now, the second step is to convert the dynamic model that you got into a differential equation. In this particular example, it's quite, luckily, it is just easy. So all you have to do is you have to just write the x double dot as the double derivative of x, and then x dot as dx by dt, and immediately you get a differential equation. But if you consider something like a humanoid robot, for example, it has a lot of joints in it. So it'll have a lot of free body diagrams in it. Then it'll have a lot of equations in it. And it might be a difficult task to convert all the equations of motion into a differential equation. But in this case, it's just easy. But I'm just giving you the general methodology. And then what you do is you take the mass to the other side, and you get a differential equation, which is kind of, if you're good at math, you would identify this as something, an easy one. So what the whole step that you would be doing here is that you take the governing equations, and then you produce differential equations of motion of it. If you're having multiple links in your robot, you would ideally have a set of 5, 6, 7, 8, 9, 20 differential equations, and that's okay. That is a way. And then the next procedure is to convert whatever the differential equation you got into something called linear time invariant state space system. This is a very famous representation that is complete, very often used in control systems. So if you look here, these are all variables of time, u of t and x of t and y of t, where y is the output of the system, x is a hidden state, and u is basically the input to the system. So, and here A, B, C, D are independent of time. So this representation, if you can take a differential equation, and if you can get to this form right here, then you're saving a lot of stuff inside the controller design. So now we'll see how we do this. So previously we had a differential equation, and now we are going to convert it into this form. So hold on for some more time with a little bit of math. So what we are going to do is we are first going to write x, capital X, which is basically a collection of two things, which is one is x1 and x2, where we define x as x and x2 as x1, x dot. The reason why we do is this is a second order differential equation where you have two derivative of 2, but here you have only 1. So the whole point is that we truncate 1 degree down. So what we do is we take 1 as the hidden variable and the next one as the hidden variable, the derivative as hidden variable. And then the trick is to look at what is x dot really. You wrote this down, and when you take derivative of this, x1 dot simply becomes x2, which is this one. And then x2 dot, which is x dot, it just becomes x double dot. And the easy thing is we know what x2 is, and we know what x double dot is. X double dot from the differential equation, we can simply write it down. At the end, we got something like this, x dot in this form. Yeah. If you hold on for a little more moment, what you could do is, okay, I think it's the same. Yeah, so we wrote this down, and at the end, you can rewrite this whole thing in this form, where this is a constant matrix composed of all the properties of the spring mass damper system, which is the mass and the spring constant and the damping ratio. And this is composed of x1, x2, which is actually capital X. And here you have a force as the input. And then you have another matrix called 0, 1 by m. I'm not sure how many of you see the relation between this and this. Do you? Can I get some hands? Do you? Do you see how this is going on? Okay. I can explain once more. This is x2. And if you multiply this row with this row, it just becomes x2 plus 0, which is x2. That's it. And here, what is happening is if you multiply minus k by m by x1, you basically get this term. If you multiply minus b by m by x2, you get this term. And then the last term is this one. It's simply rearranging. So all you do is you rearrange in such a way that you get these states in one way and all the constants in the other, and the input here, and then another set of constants. The reason why we do that is immediately you will be able to recognize this form as something that looks like this, where A matrix is this one, B matrix is this one. The input that is going into the spring mass damper system is literally the force that we are applying on it, which means if you're pushing, that is the input. And then you have hidden state, which is composed of the position and velocity of it. Is this part kind of clear, or at least the direction in which this is going? Head shakes. Okay, cool. Yeah. So now what we have is this first one. We took a different. What we did is we initially had a physical system. We got the equations of motion. Then we generated a differential equation, and then from the differential equation, we are on the path towards getting a linear state space system of this form. Now all we need is the observation model. Observation model is what can you observe from the system. And I would say in this case, I'm just observing the position of the spring damper. An external agent is just looking into the spring mass damper system, and he knows the position x1. So then immediately C matrix becomes this. So all that we did here is that we took the differential equation and we got an LTI system out of it. So next step is complete. Now, there is an alternative way to do this, and that is basically through linearization. Imagine that the differential equation that you got is like highly nonlinear, and LTI system is typically linear. It's a linear representation. So what you do is you can also get the previous equations that you got from the physics part of it by doing something else. All you have to do is imagine that this is a function f1, which is dependent on x and u, where capital X is already defined. And then this one has another set of function f2. And then you have an observation model which directly observes a position. And basically, you just have to do this to get the ABCD matrices, as easy as that. So all you initially need is find this out and then take the partial differentiation around the equilibrium point. With respect to X, you immediately get A. So if you do it with B, with U, you immediately get U. And if you take the second observation model and then differentiate it with X, you get C, and then same thing with D. So there are two ways in which you can get LTI systems out of it. One is if the system is inherently a linear system, then you can derive the equation and make it into that form. The second route is that if your system is highly nonlinear, you can linearize it and then get this form. Now, the thing is, what if the system is really, really nonlinear? Like, how would the controller behave? The thing is that it is okay for the brain or the robot brain to have an approximation of the system. It need not be accurate as long as your controller is good enough to handle it. So sometimes there might be chances that a highly nonlinear system might not work, but it's okay for the system to have a representation. And all we are trying to do is get a representation of a very complicated system into something simpler of this form. That's what we are doing. And of course, linearization comes with errors, nonlinearity errors, which we hope that the controller can overcome. That's the whole point. Now, if you do that same procedure here, like say, for example, take this one and take the derivative with respect to x1, you get 0. If you differentiate this with x1, you get 0. If you differentiate with x2, you get 1. If you differentiate this with x1, you get minus k by m, which goes here. If you differentiate with x2, minus b by m goes here. This is also an alternate route of getting these ABC matrices. That's all. So whatever you saw in the previous slide can also be derived like this. Now, next step is everything that you saw is in the continuous domain. However, the robot world in reality is highly discrete. For example, these kind of functions doesn't exist as such in the robot world. You always need to sample signals. For example, all your control inputs are also in discrete samples. So you really need to discretize a continuous time model. So there is a shift between there is a continuous time model into a discrete time model. How would you do that? And now I'm using a subscript C to represent the continuous time model. What you saw before was a continuous differential equation and then an LTI model, which is also in the continuous space. And now what we are doing is we are going to change it into such a form that you can determine at t plus 1, for example, or t plus delta t, I think it should be t plus delta t. So at next time step, what would this state be? So it should depend on another AD, not AC exactly. So always remember that you need to convert this from continuous space to a discrete space, all these matrices. And thankfully, it's easy. All you have to do is take the continuous AC, raise it into the exponential, and immediately you get the converted model in the discrete space. And you can do the same thing. Please notice that this is discrete and this is continuous. So do it exactly correct. If you don't do it exactly correct, what is going to happen is that your agent is going to think that it is controlling some other system, while it's a totally different system. So it's very important to have this conversion. And remember that this is a matrix exponential operator and not a simple exponentiating all the elements in a matrix. In MATLAB, it would be EXPM instead of EXP. Basically, it is a power series opening of the whole matrix A. At the end, all you need to do is do not ever use a continuous time model in order to make a controller that is in discrete time. So keep that in mind. Now, next is to check if the system that you have is stable or not. So what does this mean by stable? Imagine that you're having a quadrotor and you're having 4 rotor velocities as input. This system might not be inherently stable. For example, we know from experience that if you give the wrong input to the drone, it would just crash land, like as simple as that. So the system is not inherently stable. So if we get a differential equation, how would you know that the system is stable or not? And it's an easy thing to do. If you are having a continuous time model, all you have to do is you have to check the eigenvalues of AC. If all the eigenvalues of AC is having a negative real value, it means that your system is inherently stable. For example, if you're having a spring mass damper system, which is actually inherently stable, even if you pull it, it would just come back to its equilibrium point. So that's kind of the guarantee. But if you're having a quadrotor and if you push it a little harder, it's just gonna topple down. So it's an inherently unstable system. And the reason why I included this part in the whole methodology is because then you know if you are screwing up the controller design or if the system is screwing up. Because if you design a controller and it's not working, it's exploding or your drones are continuously falling down, then you know that if it's a problem with the system inherently. So that's the only reason why you do this. And remember that in the discrete space, whole laws relating to control system design is different. In this case, if you have a discrete time system, then the stability condition is that all the eigenvalues of AD should be inside a unit circle, which means the magnitude of the eigenvalues should be inside that. So just do this check before applying a controller into it to just see if it's going to be a good day for you or not. So I'll just demonstrate what it means first in case of a spring mass damper system. You already saw the equation AC. AC is basically the continuous time matrix for the spring mass damper system, and I just substituted a few values here. And in this case, and I just pulled off the eigenvalues, and you can see that it's both having negative real part, which means it's supposed to be stable. And then you just apply the input to the whole system. I just applied a sinusoid, which is that there is a force that is just doing this. It's just pulling it off. And then you can see that the output, the position variation is pretty much stable. It's kind of what you would expect from a spring mass damper system if you just put a force on it. Now, I do a little trick. I just changed the B. I turned the B to be negative. And what that means is that it's a dissipative system. It's dissipating energy out. That's the physical meaning of it. I don't know if you still get it, but what happens is that immediately the eigenvalues of this A matrix has a positive real part, which is a danger zone for most of it's a nightmare for control systems. What happens is if I apply the same input force, you can simply see that it's going to 10 raised to 4 meters. Like in, I don't know, 20 seconds, you have destroyed the system. So this is kind of the dangers that you jump into, and it's easy if you already check this prior to your controller design, then you kind of know where we are going. Yeah. So next one is the core part of it, which is deriving the control law. In our case, we are going to derive it for active inference controller. And as per active inference, all you have to do is, in order to have the control, you have to follow the free energy gradient. This is the idea. And now the core question is, what is? So it basically looks like this, where the derivative of the input with respect to time is basically learning rate multiplied by the gradient of the free energy with respect to u. F is the free energy here, and u is the control action. Now, the obvious question is, what is this free energy for robotic systems? Let's say we have a task. A robot has to, or a system has to, a dynamic system has to do a particular task. So we can, in general, write it in this form, where tau is basically the task variable, and tau-g is a goal variable. Imagine in the very first video, you saw that the robot has to go to a particular goal location, which was with the hand. So the idea is that we put that location here, and then your task variable immediately becomes your position. And then this is a precision matrix. So it's basically the inverse covariance matrix of, it basically represents the degree of your need to get to that position. If you increase it high, then it would have a high preference of getting to that position as fast as possible. So you can see this as a weighting term here. And this second block is often not used in free energy. I mean, in general, in active inference designers, but I highly recommend to use this because this is actually coming out of the math. When you actually write down the Bayesian from first principles, if you write the Bayes law and apply the Laplace approximation and all that, and have a prior over inputs, you will immediately get an extra term, which is often not seen in most of the papers, but you should use this. The reason is that you don't want a controller that will aggressively go to this particular point. So imagine that my goal is to get a robot hand to a particular location here. You don't want it to immediately jump with all the energy in the world to just collide into that location. You wanted to also minimize your control action. And in control theory, they have been historically using this term, but it's so that is the reason why we need this. We need to not only get to the goal, but we also need to get to the minimize our control effort. So the whole idea is that we have a prior distribution over your actions taken, and if you put eta u, which has 0, your prior is 0, which means it is kind of like expecting your controller to not work at all, which means minimizing. And pu literally gives the bounds of how much you are allowing the controller to take, or it's kind of exploration term, let's say. If this is very high, then you're keeping tight priors on your controller, which means it's not going to take much actions. If you loosen this up with low values, then your control action is going to be bigger and bigger. Like you're going to use 100 Newton to just move an object, for example. So my recommendation is always use this and not just this. The reason is, if you see anyone just use this term, the problem is that if you benchmark it against existing controllers, it will be suboptimal. That is the reason. So if you wanted in an optimal sense, if you wanted to make a controller, you would need to go with that additional term. That's the whole takeaway from here if you use free energy. Yeah. Oh, sorry for that. Yeah. Sorry. That's my bad. Huh? Sorry, I think that was, I mean, I should have not used this variable. So it is not, yeah, I think we'll come in the coming slides. We will have the force coming inside this. Actually, this is the force. U is actually force. U is the input U is the control input that is going into the system. So just treat this slide as independent from everything I told you before. And let's not confuse with the force there. It's just that control input is U. And in the spring mass damper case, that is the force. So you're trying to minimize the effort or the force that you're going to give into the spring mass damper system if you use this in the free energy. Do I answer your question? Or? Yeah. Okay. Cool. sorry for the mess up with the notation, but it's not force. Actually, the force is U. I put a generic U. Example of priors over. Okay, so first one is, yeah. So if you put 0, for example, if you put 0 here, if you put the price 0, what it's going to do is it's going to minimize it. Next one is that imagine that you already know what kind of force you wanted to use, or from prior learning, you kind of know that, oh, this task might take 10 Newton, but just vary around it. So then you can just put an artificial thing around it and put a tighter bound on it. So if you don't know the control action at all, like you're completely new to the system, then you put, I would recommend putting this as 0 and loosening this up, like low value for PU. But if you already know kind of intuitively from prior experiences that you might be using 8, but not sure, maybe 2 Newton more. So you then put 8 here, and then you tighten the priors, which means you make the precision higher. So it's going to give you a force that is closer to 0, closer to the value you set. That's kind of the idea of it. But it's also the case that it's a balance. So sometimes it might be more, sometimes less, depending on what's in here. But the whole idea is that, yeah. Did I answer your question, kind of? Okay. Yeah. Mm-hmm. It's coming. Yeah, it's coming in the next steps. I'm gonna show you how it's going to connect with the system. Right now, this doesn't connect. That is the whole point. This doesn't. Free energy is like this whole thing that you see in the slide is kind of very generic. So task is here, but you haven't connected it with the system yet. It's coming. Yeah. Mm-hmm. 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 Yeah, about exploration and exploitation, indeed, yes, this is kind of a form of, this is exploitation per se, but I have dropped the other terms. So there are more terms here which are constants. So for continuous time, there are going to be new terms called logarithm of, so you will immediately have minus log of P2, for example, that is actually the entropy term. Exploration term. I dropped it because it's a constant with respect to U. So when I differentiate it with U, all these constants drop. So that's the reason why I didn't write it here. But what you mentioned is correct. It is indeed a balance between exploration and exploitation. But just that I dropped it, but it's already here. Since it's already here, it's kind of in between. Yeah. Oh, yes, it is. Oh, sorry. No, this doesn't. Thanks. Copying error again. Okay, thanks for that. The second one will not have a transpose. Yeah. Exactly my point. Exactly my point. Yeah, most people haven't come there yet. That is exactly the reason why I derived it, including the priors in action. Most people don't, but most people don't see that it is. There are few works that does compare between LQR. The only way you can get there is to take priors on actions, and then you immediately get LQR, which is optimal linear controller. Yeah. And that is also the reason why I'm recommending to use this for all future active inference works, because we don't want to be underperformed by optimal control, and then nobody would care about active inference and control domain if you don't at least be an optimal controller. Yeah. This is going to be action, and this part is going to be on the task. So, yeah. Cool. Thanks. That was a nice slide. So the controller is this one. Control equation is this. And I think we already discussed this, the role of prior distribution over the control action. So basically, PU is allowing the controller to explore a little bit. So you can, yeah, I think we discussed this point. Next point is that now we are going to open, we just need to have the control law. All you need to do is find out this thing. If you have this gradient, you're done. You're done. So how do we get this? So what we can do is free energy, as you know, is not just dependent on you, but it's also dependent on tau. So you apply the chain rule and you bring in tau. So free energy is first dependent on the task variable, and through the task variable, it is linked to you. And at the same time, it's also linked to you directly. Now, about finding all these things. So there are two differentials here. One is this one, which you can, I think this is pretty simple for you, probably. Just differentiate it with tau and you would immediately get this term, for example, because it's a quadratic one. And then on this side, you would get this expression. This is clear, right? It's a straightforward differentiation. And now the only thing is this one. Anybody has a clue where will this come from? For example, this is a very generic equation, and this is coming from, like, it's just this term. And this is also always this. Do you have any clue where this is coming from? Where the task variable is related to your control input? Where? Knowledge of? So where would you get this gradient from? The gradient of or in short words, how would you know if I apply a particular U, how much the task variable would change? Yeah. Yeah, kind of. So let's say it directly comes from the system. So this is the system dynamics. So let's say it's going to be a combination of all those, but at the end, this term is what represents the dynamic system. This term is what connects your system with your controller. Yeah. It could be, yes. In a task, yeah. In case of, yes, in spring mass damper system, yes, it should relate to position. So it becomes dx by du for a position. If your task variable is to take it to a particular goal position, yes. Okay. Yeah, in this case, tau is, it need not be actually. Imagine that you have a system here and you're now going to not control position, but velocity. Then your task variable becomes dou x dot by dou u. I would say it just can be any task you wanted to do. The only condition is that you should have an expression that relates this u with your x somehow. Like it will be, because it's a physical system. If you apply an input to it, it should directly change the task variable. So that task variable could be position, it could be velocity, anything. In this particular case for spring mass damper system, of course, it is a position, but I'm also doing both controllers in this module. So we can see both of it. It's coming. Yeah. Yeah. So at the end, for all controllers that you design, you need this. That's, yeah. Okay. Yeah. Toes usually torque. Yeah. True. Yeah. Maybe I should change it to task T and not even T. But yeah, I'll change it somehow. Maybe I just use tau without thinking probably. But yeah, maybe it's not the right one. Maybe you should have a proper notation for the whole community maybe. But yeah. Yeah, yes, it has to come. It has to come from the system. So imagine if it's a humanoid robot and you just wanted to control the knee joint, just wanted the knee to follow something or your leg to follow a ball to kick, then that becomes your task variable. And if your input is your motor velocities of your joints, then your system dynamics should tell you what this changes. If you put a small change in your U, how much would your toe move? And that always should come from dynamics, and you have to somehow get it. You have to somehow get it, and it's very difficult. So what we will do here is we'll make an active inference controller to do a position control. Yeah, we have a controller here, written here. And in this case, of course, tau becomes X. now it's easier for you to follow. And immediately now that is relatable. And yeah, now things are getting slowly into your notations, I guess. What we need here is dou x by dou u. So I'm going to make some approximation. So the thing is, you simply can't get dou x by dou u simply because you need to make some approximations to get this. So in this case, what I'm going to do is I'm having a position control, and I'm going to make few assumptions about the velocity. So you remember this expression? What I'm going to do is I'm going to differentiate it with u throughout. So u goes from here, and dou x by dou u immediately appears. So these are the tricks that you would want to do with your system. Take the differential equation, do something to get dou x by dou u, because you need that here. And then since it's a constant, since it's a position control problem, what I'm going to do is I'm just going to put this as 0, which means the agent is thinking that he is not going to control the velocity. Instead, he's just going to control the position. So immediately, if you do that, if you take that assumption, you're immediately having a constant value for this whole thing. So that's it. You just take this and put here. You already know what this is. You already know what this is. You have the control law. That's it. Yeah. You mean this one or this one? Mm-hmm. Oh, sorry. This is dou. Okay, this is dou x by dou u. It should all be dou. It should all be dou. Yeah. I think it all should be dou. I'm taking partial differential word. I think it's a typing mistake. Sorry for that. It's a partial differentiation over the entire equation, and then to basically get this dou, it should be dou x by dou u. Yeah. So sorry for that. I have typing mistakes here. So, and then all you do is you substitute all these values. You got dou x by dou u from here, and you have dou f by dou x, which is this term, and then you have dou f by dou u, which is this term, and you have your control already. That is the control law. That is the control law to control kind of any active inference, any dynamic system on a which can be linearized. And to do a task, to go to a particular position, kind of, you can use this for generic purpose control, I think. But with be careful as well, because yeah, it could be nonlinear systems. Okay, next one, I'm going to do a velocity control on the same spring mass damper system. So the task is not to go to a particular location anymore, but it is to go pull it with a constant velocity. Yeah. This is more kind of an exercise to get you to design different kinds of controllers depending on your task. So I'm changing the task again. So here the task becomes your x dot, and then we need a new derivative now. And your free energy is immediately changed because your task is different right now. Your task is to get your velocity to a particular goal velocity. And yeah, of course, minimize your control effort. You can also think this of as performance and control effort, control cost. So this is a performance metric. And again, the same procedure, dou u dot blah, blah, blah. And then I take another approximation here because you need this term, right? I think you need this term. So I'm making an approximation on this where I say it linearly depends on both of them. So the thing is, you always need to make one assumption or the other that is okay for the kind of task you're doing. So I'm making a one-to-one relation between both, and you immediately get this expression, and you substitute that in your expression as before, and you immediately have a new control law. Yeah. And you can hear more about this in my talk tomorrow on Friday, maybe. It's this work. It's going to be presented here. Yeah. So it would mean that your position, I mean, it would mean something like that when you apply a particular force, your position, since it's a velocity control, I'm just assuming. So it's like saying that your brain is assuming a particular reaction to its own actions on the world. Where if you apply a particular force, it is going to move linearly along with it. So if I move it by, if I apply a force of 1 Newton, it would kind of move 1 meter or something like that. It's just thinking something, but the whole point is it is a wrong assumption. It is of course a wrong assumption, but the thing is, in assuming it, you can. If your controller is fast enough, you will catch up on the error. That's the thing. Even if you make a mistake in what do you call getting the exact value of this doesn't exist. It really depends on the time. Like so you need to approximate how your controller is going to behave. Your controller is going to behave in such a way that if you apply a force, it's going to move along with you. So that is kind of what you're saying. Kind of, yeah. Yeah, it is kind of overparameter because, yeah. Yeah, probably. Yeah, probably. Actually, yeah. Yeah, you can have, I mean, it's not that different. I tried a few and it's all working for the moment, I think, which means that the controller is capable of making enough assumptions and it still will operate. That's kind of the intuition at the moment. But yeah, you are free to make it 1-0, for example, if you don't want the next one, for example. But the whole point I'm making here is that in order to get this, you might need to make an assumption about the other one that is left, mostly. And the last and final step, we are not done yet, by the way. We just need, we got the update rule, but we thought we would be done. We need to discretize the control law for discrete time updates. The same reason I gave before, you can't use a continuous time update from the previous one into a discrete time world because this expression lives in a continuous domain. But if you need to know how much additional force you have to apply in the next step, you have to discretize this because this is also at the end a differential equation. Like this has to be discretized. And often in active inference literature, you would see something like this, where the next u is basically obtained from the gradients multiplied by time, which is actually first order, which is actually a first order approximation of this stuff. Actually, this stuff. Oh wait. I don't know where to point, but I think this stuff, du by dt, if you make a first order Euler approximation on this law, you would immediately get this. And I have encouraged you to linearize systems before, but I strongly recommend you not to do this for controller design. And the reason is that it's okay if you think that your system is simpler than how complicated it is. Imagine that you have a very complicated system. It's okay for the agent to think that it's a kind of linear system, but it's far more worse to think that your controller is linear, because your controller is something that should be catching up with all the errors you made in the past with your modeling. If you make a modeling error, your controller can catch up with it. It should be able to catch up with it. And instead, if you use Euler method and discretize it like this, you would end up in problems. In the next slide, I would show you why I would strongly not recommend this. Almost all active inference papers on real world application, they are using this, but I would tell you why you shouldn't do it. What you should do instead is some better method. It looks a little bulky, but it's very handy. All you need is two unknowns. It looks a little bulky. All you need is two gradients of free energy, and you might reach somewhere close to an exact discretization. I'm not claiming that this is an exact discretization, but it's much better than Euler. Euler method uses first order gradients of f in order to compute the update for you, which means what your next control action is. But this one uses two orders. It also uses the information about the curvature of the graph that is going. Imagine that you're going down the free energy curve, and at some point you have the gradient, and this law basically uses that gradient to go somewhere. While this law uses the curvature information about how curved your thing is, and then take much faster decision into jumping into that local minima. That's what this is doing. Depending on the learning rate K, it would just immediately jump into the optimal. So this is much faster in the sense that of reaching the optimality in a faster time frame. Also, it has an advantage of not blowing up your solutions because you're quicker in the solutions. Euler has a very bad history in Euler method has a very bad history in discretization problems, which I'll show you in the next slide, trying to convince you. But here, what I'll do is I'll discretize the system for the position controller. You're already familiar with this one. I would use the first gradient. We already derived it. For the second gradient, all you have to do, I mean, it's just gone. Immediately you would drop this and you will have a copy of this here. That's it. Yeah. I can't hear you. Oh, yeah. Yeah, sure. Go for. Uh-huh. Yeah. So, I mean, you can use any other discrete. I mean, I would highly prefer Rangekota as well. Rangekota is one of the strongest and widely used. It uses 4 or 5. I mean, as per the order, you can use trapezoidal methods are there. But I would recommend Rangekota or this one for active inference problems. It always solves for me. So I'm pretty confident with it. That's why I put it here. But of course, free feel to use other discretization methods for controller, but make sure that you use one. Like, don't jump into this because the moment your time steps are small, none of those controllers will work. None of them. If you do this, because if your differential equation is by default stiff, then you are already running into problems very quick. So either use this. It used to work with all the free energy stuff. Also go for trapezoids or Runge-Kota. Yeah, sure. But make sure it's not one gradient dependent. And going on to the velocity control, you immediately can write that as well. It's just a copy of this whole term over here and drop this. So so at the end, you don't need to do additional stuff. You just need to change your control law into something like this, and you immediately have a better discretization. And this is where I'm trying to convince you trying to convince you not to use the Euler. If you look carefully, this one is Euler. And the plotted here is a step size. It is also for the damped harmonic oscillator, which is actually the spring mass damper system itself. Here, I copied it from a website. But yeah, the idea is that they used a lot of different methods like Euler, Heinz method in approximation. This is Runge-Kota, blah, blah, AD. I don't know what these are, but it doesn't matter. Whole point is that if you look here, if you increase the step size, we are talking about 0.0001, 0.00, like 0.1 seconds step size. For us, step size is time. Because it's a dynamic system, our steps are time. So if you take just take 0.101 seconds and look at the difference in the error. This is absolute error. And you can see that Euler is already gone. It's gone. It's no way close. And these methods are in the range of 10 raised to minus 20, like almost zero. So I highly motivate you to not use Euler, because if you see an Euler in a paper, and just ask them to decrease their time step. And yeah, you will take them here and see the magic. Yeah. So to wrap it up, I don't know what time it is. Oh, we are on time or so far early, or I don't know. Yeah. Okay. Yeah, so I'll just wrap. So these are the steps. So you finally got the discrete control law that you wanted to put. Yeah. Mm-hmm. Yeah. Answer is yes. My whole PhD topic goes on that. So it is to use free energy principle to learn the whole ABC matrices from data. So you can do that through free energy principle as well, but it's not a controller anymore. It'll be it's in control theory, it's called system identification. So you have to do, so you can develop. So I have, I don't know if you're familiar with DEM. So it's a dynamic expectation maximization algorithm. It is a variant of Friston's work as well, based on active inference with parameter learning. So you can search up on that dynamic expectation maximization algorithm. And I have some papers on that, on how to get these ABC matrices from data. Yeah. Mm-hmm. In uh, you can actually do any of those. I would strongly recommend a physics-based system where you go and weigh the spring, where you do some experiment and get the K value. But it's often not possible. So you will have to use some system identification techniques to get these values. But I would strongly recommend the physics-based, because the whole framework was for dynamic system. But you're free to also use it. Like, so there are different methods in system identification, like subspace methods and prediction error maximization. There's DEM from free energy principle as well. So what I would recommend is you can always approximate a very high nonlinear system. You just imagine that it is going to be a standard LTI system, and then do the system identification on that, get these ABC values, and then you need not do the first few parts. You can just cut that off and then start from discretizing that system. No, no, no. No, it doesn't. As long as the values are right, you need the values to be right. Even if your model is a little wrong, I think the controller will catch up, because we are not probably exactly using we are linearizing. So as long as your controller is good, it will catch up. Yeah. So some other question. Yeah. Okay. You need to know everything about the system. Uh, yeah, that's a good point. That's a good point, actually, because in order to have a controller, you need A/B matrix, for example. So you need to learn that. Yeah, that's what you meant, right? Or like that. Okay. Mm. It's very complicated to answer that question, actually, because there doesn't exist one. I mean, per se, there doesn't exist one gradient, because it really depends on the problem. Like even if you learn, it's going to have multiple. It's not going to generalize, because if you take a two-DOF arm, for example, you can apply different things to it, and the gradient would be different. That's the thing. It's mapping to. It's not a one-to-one mapping to be generalizable. That's kind of what I think it is, at least so far from how I think about it. It's not a one-to-one mapping. There's multiple mapping for the same gradient. You can change, like, for example, at a particular configuration of a robot arm, if you apply a small torque, it might make the end effector move much different than how you would with a slightly different torque or slightly different configuration, or even the same configuration but with different starting point for torque, for example, or different rate of change of torque. Or so all these are multiple mapping, but there is a possibility, of course, you can. But yeah, I haven't explored that at all. Open to you guys too. Yeah. Yeah. Oh, I have no clue how to do that. No. Anyone? Do you know any? I haven't even touched that topic. No, usually not switching. No, not me. Me neither. I have no idea. If that's why in the beginning I said, if you bring it to LTI system, we are so happy because we can do all these things. All you need to do is this gradient, these gradients, and we are done. We are done. We are done with the whole thing. Mhm. Yeah. Yeah, so that's the thing. That's a good point. So the linearization is always taken around the equilibrium point. And when you're far away from the equilibrium point, you do have non-linearity errors piling up, which is exactly what you mentioned. It's called the non-linearity error. So imagine that if your hands are down, this is the equilibrium. And when you linearize, we always linearize around the equilibrium point. And as you move further away from the equilibrium point, the nonlinear errors accumulate. So that's the reason why this would be different. It does, but the cool thing is that our controller is good to catch up. So your system can be a little not okay, but still, if your controller is good enough, you can catch up, kind of. But yeah, I agree. It wouldn't be optimal. It will still be suboptimal controller. Like the best thing to, of course, do would be to have use the nonlinear model, have a controller written for the nonlinear model, etc. But this is kind of in the tutorial material, I was kind of giving the easiest way for you to control it. But of course, it would be suboptimal than the nonlinear controllers. Yes, for sure, like MPC or something else. But the point is that I agree with your point. It is going to. Mhm. No, it would. I think it would go up. Yeah, I'm telling you this because a simulation is coming, where I think I changed all the values and it's the same problem. I changed all the values and kind of it worked. I mean, it does work. So that's why I said it works. Okay. So the steps, recapping the steps, first model the motions of the system, which is basically the resolve and find out the free body diagram and all that. Convert the dynamic model into a differential equation, and then convert the differential equation either into an LTI system or linearize the whole thing to get an LTI system. I only mentioned LTI system because it's an easy linear controller. In the tutorial was a linear controller. Then discretize the continuous time model to get a discrete time model, which is about the ABC matrices. So AD and AC. Check the stability of the system if it's inherently stable or you have no hope on it, or for example, derive the control law and then discretize the control law for continuous discrete time updates. At the end, this is what I promised you. It's a 5-line code, kind of shorter 5-line code that it's basically this one line and 1, 2, 3, 4. That's it. So I just wanted you to look at what's going on. First, you define the model in the continuous space. So this is ABC matrices. Then you're defining all the constants that you wanted for the controller, which is PA, PG, and a goal. A goal, I'm saying that go to 0.5, position of 0.5, and a few time steps and NT, blah, blah. So this is how you discretize the system in MATLAB. It's just one line. So it's basically C to D, which is continuous to discrete. This is the whole state space model, which is SS. Give the DT as the time steps. And this is zero hold, which you don't have to care at the moment. So the whole thing is that in one line, you can discretize the whole system. And you run a loop through time. And you absorb two gradients that I told you, dou F by dou A, dou U in your case, dou F by dou U, dou F by dou U, dou square F by dou U square. Two gradients. How do you get the gradients? You do what is the brain's estimate of X and where do you want to go? Multiplied by transpose and multiplied with a constant, which is the precision, your goal precision. How with what variability do you want the goal to be achieved? And then the inverse of A and B. This is for the position task. And then PA into the control action A. And then you get the second derivative by copying this part into the first one as well, and then removing the U from here. This is the linearized control law where the ith one is computed from added from the previous one, and you're using exponential metrics over the gradient into dt, blah, 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 blah. In this case, this is a controller part. This line is the controller part, and this line is the generative process where the core thing is that here you're using a continuous A. If you're using the continuous expression, you have to use the continuous A. If you're using the discrete expression, you have to use a discrete A. Keep this in mind. If you flip it up, I'm not sure if it'll work anymore. So make sure that this is also the reason why I'm again emphasizing on why you need to discretize your system. So you use discretized systems A, and then roll out like this. Few caveat, I haven't handled noises at all here, which is very different. I haven't also mentioned estimation, which is also important. Both of those factors should also ideally go into this, but since it's a tutorial, I skipped that part. But yeah, noises on the system is gonna be a whole different problem. Estimation, you can already do it using free energy principle, but I'm skipping it. I don't know if this code will run per se, but you can get the running code from here. And this will also be the main talk. I think on Friday, I'm giving a presentation. So if you, and I'm using these things to do something else. So yeah, you can always follow up. On the simulation side, this is for the position control. It starts from 0, and whatever is plotted here is time. And then this is a goal that you wanted to go with the spring mass damper system, and it just reaches there. And this is the control force you apply. As you can imagine, if you wanted to take a spring mass damper to a particular location, what you have to do is you have to increase the force and then stop and then hold on. Why do you want to hold on? Because if you drop it, it'll just go back. Like you're having a spring mass damper and you apply a force and bring it to a position, and you have to hold on to that position. That's exactly what you see here. You're holding on to that position. So it's correct, kind of. And in the velocity control, your goal velocity is this one, and then it just goes to that particular velocity, and you keep applying a constant force, like, not constant force, increasing force, so that you can move as long. I mean, this is an approximation because you can't stretch a spring mass damper system this much, but this is a kind of a theoretical problem that we're dealing with. You can indeed use active inference controllers to do these things. Do we have enough time? How much do we have? Okay, we are done. So I'll just show you some videos quickly go through some videos on using the exact same things that I've shown you on robots. For a quadrotor flying in this work, for example, on modeling, I basically linearize the system where you can, these are the roll angle and roll velocities here. And the input is basically the PWM signals that is going into these rotors. And the model is basically something looking like this after linearization. And here's the input torque, and you're basically measuring the roll velocity. So it's kind of, I'm just giving you a glimpse of how you could use everything that you saw here into different robotic problems, for example. So this is on the modeling quadratic LTI systems. You can see the extended work here. This is for active inference for robot navigation problem. I have used the exact same rules and update rules that you have seen before. Like nothing has changed. The goal is that this one should go here, this one should go here, this one should go here. You have free energy written down exactly like that, with an additional term where I say, do not hit this. That is also on the free energy. And then immediately, this is kind of the thing you get. For static obstacles, and I have a free energy curve. This is plotted for this agent right here. And when he looks, there is a bump on everyone else, like, because everyone else is also an obstacle because I shouldn't hit him. And then if you minimize the free energy, you would simply go to that desired location. So I think it is for this guy going here. This guy is going down here, something like that. If you look at the dynamic obstacles, the whole problem here is symmetric swapping problems, where this drone is to go here. Like they have to, sorry, this is non-symmetric swapping. And whatever you see here is exactly the code that is running here. Nothing has changed. I haven't hard-coded anything into this. It's the same code that is running here, applied here. And whatever you see is kind of an emerging behavior from the equations naturally. This is not a hard-coded one. So all of them understood that they have to keep an immediate distance between each other because he's an opponent. He's also an opponent in collision. So they kind of have a vector in this direction to finally reach the goal, for example. And if you see what all I put in the free energy, all I changed in these from the previous, all the tutorial you saw was the free energy expression, nothing else. The free energy expression changed where the task variable now is x. I need to go to a particular x. I need to go to a particular y value, like an x coordinate and a y coordinate. In this case, I need to go to x coordinate and y coordinate of this. And that becomes your goal, free energy for the goal. And then I have two additional terms for obstacle avoidance as well, which I'm not discussing because of the time. And I solve, what I do is I make an approximation. So the thing is, you can have the dynamic model or you need not have it. In this case, I force the brain not to think about the model at all, like model free. And I put this as unity, one, just one. And then all I have is this law, which will apply for any free energy minimizing scheme. And immediately you get it working. So you can have the model or you need not have the model. Sometimes I won't recommend not having a model, but it works. That's my whole point. It does work. This is how you can solve for no robot navigation problem. All you need to change is the task and your corresponding gradients you have to absorb. That's it. This is multi-robot navigation information. Exact same code from before. I'm adding an additional term here, which is that the distance between two robots are basically the Euclidean distance between them is trying to be the same as the initial one. So I start the simulation with the drones in a formation, and then the whole agent is trying to keep that formation. That's it. So you have this free energy and you add it to it, compute the derivative. So you will take the derivative of this and put it in the control law, exact same procedure that you did before. And you end up in something like this, where there is a goal. There are three things happening here. There is goal directed motion. There is also obstacle avoidance because they are not colliding with each other. And at the same time, they are keeping a formation, which is equidistant, maintaining the distance between them. Yeah, so I add an extra term, which is this. This is also the same simulation, keeping formation, but with one twist, where this thing is relaxed. I'm relaxing this one a little bit with a lower value, not high precision. Immediately, you can see that your formation is capable of what do you call splitting, because it is not a tight. Since these relations are not tight, you can escape. For example, if a group of drones are stuck inside a room and wants to escape, it has to reorganize itself to escape through the window. That's kind of the scenario here. And this one is for 2 degrees of freedom robot. It looks very simple, but it's highly complicated to solve its differential equation to get to solve. So this here, what you see here is with the physics in it, with the whole dynamics in it. And this is with active inference controlling at 2 degrees of freedom arm. Exact same kind of methodology that you saw in the tutorial. All the things were done exactly like that. Yeah, and this one was without the physics. It was an attractor, but this one is with a physics aware. I would always recommend a physics aware because if you wanted to use active inference to solve some hard problems like humanoid walking or something, you really need to know the system dynamics. Because attractors could simply take you a straight path. Attractors always attract to that path, but the problem is sometimes that path is not the right one. Like there will be something there, and if you are unaware of the physics of it, you would never see it. You would think that, oh, I can just straight go to my goal. But sometimes going straight to the goal would just make your leg unstable and you would just fall because you don't know the system. If you don't know the system, you can't simply go to the goal. So always go for that. And I would like to thank my supervisors, Martin Visser and Pablo. Yeah, any questions?